standing waves can be, what I've showed here is a picture of an actual water wave. And for the boaters out there, you've seen standing waves out in the water, waves that just kind of go up and down. They don't travel left and right, but they just kind of go up and down. And it's because one boat passes in one direction, one boat passes in the other direction. They create waves that interfere, and you can actually see at the intersection these standing waves. And that's exactly what's happening in a transmission line. So very briefly, we have a forward wave, we have a reflected wave, and then we have a standing wave. Down here at the bottom, if you really want to kind of see a good animation of this kind of explains it to you. And I'd recommend you copy and paste this into your browser and just kind of take a look at it and get a feel for what the standing wave is. With a perfect load, if we terminate in the characteristic impedance, remember there is no reflected wave, so therefore there is no standing wave to create an interference pattern associated with either. Well, here's what they made me do. All right. We didn't have, we actually did, but they were, we had network analyzers. I'm not that old, but the one way of measuring the standing wave ratio is what they call a slotted line. You can take a coax and you can rip a slot through the shield over here. And then you could take an RF voltmeter and you could probe it and search along the line with your probe. And you could find a voltage peak and you can find a voltage minimum. And the difference, the divisor, you divide these two numbers together and that's your standing wave ratio. It's the ratio of the peak voltage to the minimum voltage. It's as simple as that. Now there is such a thing, I'm pointing on the wrong screen here, my apologies, but there is such a thing as a current SWR, or called ISWR, but it requires putting itty bitty little ammeters along the way, which is really tough to do. But it does exist, and it's something that you should be aware of. The ISWR is 180 degrees out of phase with the voltage SWR. So it's appropriate just to call it SWR. And if you want to impress your friends, you can call it VSWR, VSWR, just to show your buddies how smart you are. But it's really just the standing wave ratio. Now, the other way, which came a little bit later on how to characterize it. By the way, remember, once I know the standing wave ratio, I can make some judgment about what the input impedance of my line is. So this is one way of measuring it. I take a slotted line. Now, of course, a slotted line, this is done at very high frequency, so that the wavelength is very short. But the slotted line now, the slotted line has
quiet.
Yeah, quiet. The slotted line has a, it might be very long. It might be 100 feet long at 20 meters, for example. But anyway, since you don't really have that, you don't really need to. Now, a man by the name of Bruni came up with a really cool way of doing this. And he kind of took I don't know if you know what a Wheatstone bridge is, but it's kind of a balanced cube, and you measure across it and everything balances out and cancels out. A Bruni bridge is something that you're very aware of. It's what is used in your bird watt meter. It's what's used in your SWR, your little $25 SWR meter. It's a directional coupler by another name. And how it works is an amazing little fun task. And if you ever want to understand how your directional coupler works, Google the term Bruni bridge, and you'll come up with all kinds of explanations. But the point is, you can put a Bruni bridge in, two of them in line, and orient them in opposite directions. And one of them will measure the forward power, if you will, and the reverse will give you a voltage that's related to the reverse reflected signal power. And once again, we can calculate from that, we can calculate what the VSWR is, and from that we can get a feel for what the input impedance is. Now you can work all this backwards, by the way. So if you knew what the input impedance is, which you do now with your impedance meter, If you knew what that was, you can calculate the SWR from that. And also, you can calculate the difference between the incident signal and the reflected signal. That difference is called return loss. So think of it this way: you have 1 watt going this way and 0.1 watt coming back. You can think of it as a loss. Well, I've lost 9/10 of a watt here, right? A little pause there. We've lost 9/10 of a watt. So you can kind of think of the reflected wave as a loss. Now, it's not a true loss, and I'll get to that later, but you can think of the reflected wave as being so much below the incident wave, and that is what we call return loss. It's always shown as the 10 times the log of the ratio. And we do that for convenience. So when you say 20 dB of return loss, what you're really saying is that the reflected wave, the magnitude of the reflected wave is 20 dB below the magnitude of the forward wave. And that's actually, if you put in the numbers there, it's actually a pretty good SWR. So once again, SWR can be related to input impedance, as can the ratio of the forward and reflected wave can be measured related to the input impedance, and you can work that backwards. So from the input impedance, I can tell you what the SWR is, I can tell you what the return loss is. And it's really quite that simple. Now, I just want to do a little sidetrack here. If you were to take an attenuator, let's just say we had a 3 dB attenuator, and we put in a signal into the attenuator, say 0 dBm, and we come over here and let's reflect it. Let's take this load as a short circuit out here so we have 100% reflection. So 0 dBm, go through a 3 dB attenuator, and now you're 3 dB down. All right, you get a perfect reflection off the load. You go through the 3 dB attenuator again. Now that signal is 6 dB down. So our return loss, if you will, is 6 dB because we've lost 3 dB here and we lost 3 dB here. Total is 6. Now, when you look at, I'm going to show you a chart in a second. 6 dB return loss is exactly 3 dB SWR. So you might think that, oh, okay, my antenna's 3 to 1 SWR is not all that bad, okay? But if you have a 3 dB insertion loss in your coax, you can have a short circuit for an antenna, and it's not going to work very good, even though you're only measuring 3 to 1 SWR. So your coax loss acts the same as the attenuator and will make your antenna look a whole lot better than it actually is, which is why you want to do your reference plane as close to the antenna as possible on a lossy line. So don't sweat the math. There's charts available, there's calculators available, everything. Just remember that the magnitude of the SWR and the magnitude of the return loss, those two numbers don't have any relation to line length. You can measure your SWR anywhere along your coax line, it's going to be the same. You can measure the return loss anywhere along your coax line, it's going to be the same. What differs is the input impedance. And that's really the only number that matters. But you know something, you can measure your input impedance and calculate all this other stuff. But that's what your VNA does for you. You don't have to do it. So just for completeness, 2-port networks can be characterized. Now this is away from the VNA, but 2-port networks can be characterized in any number of different ways. And when you do a deep dive into it, this is what my college course was all about. But you can go, there are Z parameters, H parameters, Y parameters, S parameters, A, B, C, D parameters. There's all kinds of different ways. Z parameters are intuitive to us. H parameters are good for characterizing transistors. S parameters for RF networks, and so forth. Each one has its place. You don't really have to worry about it. The one that we're talking about here, and the one they often just say is S11 and S21. S11 is the input port voltage reflection coefficient gamma, capital letter gamma here. All right. wow, what is that? Well, the gamma is just related to our impedance changes here. So if I can measure the impedance at the input, I can calculate gamma. And you know something, you don't have to worry about it because your VNA does it for you. Wonderful little device. That's why you paid the big bucks for it. So from gamma, you can calculate the SWR, you can calculate, and from S11, you can calculate the return loss. They're all the same thing, only different. So different in what ways? Look, Google it. There's all kinds of return loss to VisWAR conversion tables. Let's just pick a SWR here of 1.5 to 1. That equates to 14 dB of return loss. 1.5 to 1 equates to reflected power of almost 4% and a reflection coefficient of 0.2. So if you have to know all these numbers, they're there for you on a chart. And your VNA is taking this chart and just converting it for you. All right, so that's enough on the TX port. I'm just going to do a very brief talk about the other port here. And the other port is the receive port. And I'm talking about here's your transmit port, here's your receive port. And if you want to measure the insertion loss of a filter, the way you calibrate is you take a jumper and you take a jumper between these two ports and you calibrate out that, and then you add in this and you have your insertion loss. So you might get, if you had a low pass filter, you might get a graph like this, or a high pass filter might give you a graph like this, a band pass filter like this, and a notch filter like this. Essentially, that's all the other one does. And it's actually very simple compared to the transmit port, what it does. But now you can completely characterize your two-port network. Now, the big machines also put signals into the output, complete characterization of all the S parameters, H parameters, Y parameters, and all of that kind of thing. And they do it automatically at a push of a button. That's why you pay the big bucks. But if you wanted to fully characterize your two-port network, you have to take it and you have to turn it around so that you can measure the output impedances too. You will never have to do that unless you really get into big time circuit design. I wouldn't even worry about it, and I'm not going to say anything more about it. So your analyzer measures impedance. It's pretty much what the TX port does. Think of it that way. It's an ohmmeter on steroids. From the input impedance, it can calculate SWR, return loss, the magnitude of the reflection coefficient. But in order to tell the rest of the story, we do need to know something about the length of the line. Now, on mismatched coaxial lines, that input impedance, remember when I said there were 2 points that gave you the same SWR? There's actually an infinite number of points that give you that SWR. And we call that infinite number on the Smith chart that the locus of all those points, the sum total, if you will, of all those points forms a circle. And you'll sometimes hear people saying, well, we're traveling around the VisWAR circle.